It's such an honor to be here. I regret that I never met Richard Feynman, and I think it's the definition of legacy that he continues to have such an impact on the generations that follow him. I was asked to speak about the gravitational wave detection tonight, which is obviously very important to Caltech, and it's extremely daunting to do so in front of this particular audience. Where's Kip? I want to start this story, and we'll talk about the moments where Feynman pushed the story along, looking at our own galaxy. This is our Milky Way, a collection of 100 billion stars. It is not a cartoon. It's actually a digital atlas built out of the observations we have of our Milky Way galaxy. And if you think about how remarkable it is that on this silly, insignificant little rock, we've barely gone to the moon, that we're able to see so much of space just by sitting back and collecting light. When Richard Feynman was born, it was not known that there were other galaxies out there. It's pretty extraordinary. It was only a couple of years after Einstein had published his general theory of relativity, which inspired so much creativity, so many discoveries, including Hubble's discovery not far from here, that there were in fact other galaxies out there, and that the Milky Way was not the entire universe, extending our universe tremendously further. He also inspired, through the general theory of relativity, the discovery of black holes. He receives a letter from Karl Schwarzschild, famously on the Russian front during World War I, allegedly in the trenches, although I think that's apocryphal, calculating ballistic trajectories, and also, perusing the Prussian Academy's proceedings of the Prussian Academy of Sciences, as you do in the trenches. And he finds this stunning solution to a thought experiment. He imagines taking a star, and it's just a hypothetical, it's a fantasy, it's not reality, taking all the mass of a star and concentrating it to a point. And he solves for the curved space-time around this object, and he realizes that it would cast a shadow on the sky, because even if light veered nearby, it would plummet down the well of what we now call a black hole. And he writes this to Einstein, he sends this to Einstein. And Einstein's very impressed with this mathematical solution, the elegance, the simplicity. He helps Schwarzschild get it published, but he doesn't think they're real. These are just imagined objects. Nature would protect us from their formation, he thought. Now, in reality, nature figures out a way. Right? There's this extraordinary ability that nature has to find all the possibilities and realize them, make them happen. A bunch of idealistic physicists discover nature's mechanism when they're doing something that many of them probably never suspected they would do, which is to think of ways to use quantum mechanics to kill people, right? This is during World War II and the pressures of the race for the atomic bomb. Many famous physicists became obsessed and devoted their time to the Manhattan Project, and of course Richard Feynman was one of them. Oppenheimer hailed him to Los Alamos, and they worked together on the nuclear physics of the time, and the nuclear physics that was powering the war effort and the atomic bomb effort. And it's also a testament to the dispassionate nature of the laws of physics, that the same laws that were at work, the same laws of nuclear physics that were at work powering the bomb are also at work in stars. Kip already referenced that Feynman had thought about gravitational collapse. Oppenheimer, also with a student Schneider, wrote this lovely paper about how stars, which were powered by thermonuclear explosions, when they ran out of fuel, would collapse under their own weight if they were heavy enough, exploding into a supernova event, and if the core that remained was massive enough, they reasoned that there were no nuclear forces that could resist the ultimate and total collapse to a black hole. Now, the publication of their paper happened in 1939, in coincidence with the Nazi advance on Poland. And people weren't paying that much attention to astrophysics that day. And the paper sort of fell into obscurity. And there were a lot of people who didn't believe that this was true. Wheeler was among them, Wheeler, Feynman's mentor, who also had abandoned a lot of his own research to work on the war effort. Wheeler came back to this problem many years later. In fact, he was very critical of Oppenheimer. He thought Oppenheimer was wrong. And after he came back to his own research with all of this information that he had learned and acquired while devising the bombs, he applied to the question of gravitational collapse and realized that, in fact, Oppenheimer had been right, that it was the prediction that heavy enough stars would collapse to black holes, which was just extraordinary. And when he gave a presentation in an auditorium like this to speak to Oppenheimer to say, you were right, I was wrong, the story goes that Oppenheimer sat outside on the benches, no longer interested in what Wheeler had to say, talking amongst friends. When Wheeler finally foisted the term black hole into the lexicon, which wasn't until like 1967, he was at a lecture tired of saying the end state of complete gravitational collapse, which he had said about a dozen times in the lecture, and apparently someone from the back of the hall shouted, "How about black hole?" And it stuck. Wheeler had this way of just using things, and then they were there. But by then, Oppenheimer had already died, and may never have really understood or recognized that his most fanciful contribution to theoretical physics was his most significant. So we now know that, in fact, black holes form. Now, black holes are massive, but they're tiny. If you make a black hole 10 times the mass of the sun, it might only be 60 kilometers across. And that's a tiny little object to try to see in our vast galaxy. How could you possibly see something that's smaller than the distance between cities in this vast Milky Way galaxy? So there wasn't a lot of hope that we would see them, at least not see them bare. If you imagine the situation of two black holes, you can't take a picture of one, you can't take a picture of the other because they're too hard to resolve in this vast, dense collection of stars. But there's something else that happens. If those two black holes orbit each other, they're like mallets on a drum. They will actually ring space-time the way mallets bang on a drum. And as they do so, they create what Einstein coined as gravitational waves. And they'll orbit together, eventually coalescing to make a bigger black hole, creating these waves in space-time, literally in the fabric and shape of space, that emanate outward, something Kip has very beautifully described as a storm in the geometry of space-time. Now, in 1916, in this correspondence with Schwarzschild, when he's thinking about black holes and dismissing them as imaginary, he says to Schwarzschild, the most important problem I have to think about now is the existence of gravitational waves. Are they real? And by real, he meant, do they actually carry energy? Or are they just a figment of the way we're describing space-time? And he writes papers saying they're not real. He writes papers saying they're real. A decade later, he says they're not real. A decade later, he says they're real. This goes on for a very long time. He writes a paper with a colleague saying gravitational waves do not exist. It is accepted for publication. Between acceptance and print, he sneaks in an entirely different manuscript, which says that they do. Somebody says, Einstein, you have to be careful. Your famous name is going to be on these papers. And he says, oh, my name is on plenty of wrong papers. Don't worry about that. And this goes on for quite a long time. In 1957, Richard Feynman shows up at a conference in Chapel Hill on gravitational physics. He registers under the pseudonym Mr. Smith. It's some kind of act of defiance. I don't know. He's disappointed with the state of gravitational physics. So he decides to go under the pseudonym. I'm pretty sure people recognize him. I don't know. He stands up at this conference and he gives a description, a thought experiment again, which is very compelling, called the sticky bead experiment. And in the sticky bead experiment, he gives this compelling argument that gravitational waves are real. It's very simple. I have a rigid rod, I have beads loosely strung on the rod, and when a gravitational wave strikes, the beads begin to oscillate. They're moved on the wave like buoys bobbing on the ocean. And they will impart some friction, rubbing, onto the stick and thereby heat it up. And that to him is the argument. You have energy transferred from the gravitational wave to the beads to the rod. That's it, end of discussion. It's actually an imaginary gravitational wave detector. And this argument is very compelling, and many people are convinced, and many people use it, many people contributed to it. But he attends a conference a few years later and is so frustrated to hear people still arguing about whether or not gravitational waves are real. But the arguments go on for a long time. Now, we come to a few dreamers who decide, I've had enough of this calculating, I'm going to go out and try to see what's out there. Now, this sticky bead experiment also has an interesting map to something like the human auditory mechanism. If you were floating hazardously close to two black holes colliding, your ear mechanism could actually ring in response, and you would hear the gravitational wave, even in the absence of a medium. Now, it's not an experiment anyone really wants to perform, and I haven't actually worked out all the details of the ear mechanism, but it's plausible. We would technically hear the wave. So gravitational waves, I want to emphasize, are not light. They're much closer to sound. And so groups of people decided to step outside and have a listen to the universe, find out what's out there. We're going to fast forward about 50 years. Experiments break out all over the world, literally all over the world. They're small experiments, some of them in ramshackle structures and tiny little things that they're building. Nobody knows exactly what they're listening for or what magnitude signals to expect, or if it's even possible, or if they're just chasing a wild dream. And what develops is the realization that the experiments have to be enormous. So here we are, after a small group began to develop LIGO, which Caltech is, of course, the center and the heart of LIGO, the Laser Interferometer Gravitational Wave Observatory. Ray Weiss, one of the original architects, says the word observatory caused them a lot of trouble. People said it's not an observatory until you observe something. And there was a strong belief that it wouldn't succeed from a large part of a respected population of astronomers, physicists. But after a kind of climbing of Mount Everest, a small team burgeons to be a team of, let's say, roughly 1,000. The experiments are enormous. Each instrument, this is one of the instruments, spans 4 kilometers. There are 2 instruments on 2 different coasts. You can tell that's Louisiana because of the unwanted swamp, in which there are alligators and bass. Nobody knows where the bass came from. I'm not going to describe the experiment in detail, but let's just call it, it's like a giant cosmic microphone, and it's just listening to the skies. And the aspiration is that a signal will come. Now, I described the black hole signal, which was very leading, but in August 2015, Ray Weiss said to me, if we don't detect black holes, bear in mind he's spent half his life on this, this whole thing is a failure. That's what he says. And meanwhile, at the same time, everybody in the experiment is telling me, oh, we might never detect black holes, never, or they'll be last. The only person who said otherwise was Kip. Kip said black holes are going to be first, and he just said it and smiled. The idea would be that whatever created this ringing of space-time like a drum, when it swept over the Earth, it would be recorded by one microphone in Louisiana and another in Washington State, where the other instrument is. Now, this was August 2015. In September 2015, the advanced detector has been assembled. It's been an arduous climb, incredible technological achievement, undisputable that the technological achievement had been made, but we just didn't know if nature would provide. And I should emphasize, I'm not an experimentalist, so I'm a theoretical physicist, so everything for me happens in pen and paper, in the mind, and I, no question, developed a crush on the experiment. I would just walk into the lab just to watch how kind of space station slowly people operated and how everyone seemed to know what was required next, and the sort of strange sense of this kind of ant colony organism coming together to make this tremendous instrument operate. Now, while this is happening, September rolls around. Meanwhile, 1.3 billion years ago, two black holes, each one about 30 times the mass of the sun, were in orbit together. In the final stages of what might have been a very long life together, they emit the loudest of their gravitational waves and eventually collide into a quiescent black hole. You have to imagine that when these gravitational waves were generated, multi-celled organisms were just differentiating on the Earth. By the time they hit a nearby star system, Richard Feynman was born, and general relativity was published. By the time this wave was in the interstellar medium on its way about a distance from our solar system, the LIGO scientists decided, in fact, they were not ready to perform science runs, that they still needed to tinker with the instrument and develop algorithms. By the time it was a solar system distance away, the distance of Jupiter, they were hammering on the instrument, interrupting it, taking it offline, braking on trucks on the access road to see what effect it caused to disturb the instrument. By the time it was nearly the distance of Mars from us, they became exhausted. Fortunately, it was the middle of the night in Louisiana and in Washington State, and the experimentalists on site decided, that's it, it's time to go home. They put their tools down, mercifully leaving the instrument in detecting mode, and go home. Within the span of 1 hour, this gravitational wave, which has been traveling for 1.3 billion years, strikes the instrument in Louisiana, is recorded beautifully. Then it hits the instrument in Washington State, is recorded beautifully. By the time people wake up to check the logs, it's already billions of kilometers on, somewhere else, for another civilization to detect, somewhere else. Rightfully, there have been several detections since then. Rightfully, the entire LIGO collaboration won the Breakthrough Prize in Physics for the accomplishment. Ray Weiss, Kip Thorne, and Barry Barish shared the Nobel Prize in 2017. Can I give them a little applause? And here we are now, really on the precipice of a completely new world. That gravitational wave detection, that first one, was the most powerful event ever detected since the Big Bang. Yet none of it came out as light. And it came to us as the faintest echo. It rang the machines by less than 1/10,000th the width of a proton over 4 kilometers. Okay? It was the faintest echo when it hit us. It's quite a remarkable achievement. It was also 1/5 of a second of what might have been a billion years together in orbit that was actually detected. This is a map from the digital Sloan Sky Survey. It is a map of actual galaxies. Everything you're seeing is an entire galaxy. There are as many galaxies in the sky, observable universe, as there are stars in our galaxy, and each of those galaxies might have billions of black holes. And so here we are at a time where we're recording essentially a soundtrack to this beautiful silent movie we've compiled of the universe. And of course the excitement, and I remember when I was a student listening to Kip talk about this ambition before it had been built, before it had been funded, what I was so excited about, and I know many people were, was the prospect of hearing something we just had never thought of before. I mean, after all, when Galileo pointed a telescope at the sky, he did not predict black holes and quasars, let alone galaxies, collisions of galaxies, that there might be an entire dark sector of the universe that we can only listen to. And this is where I find Feynman's legacy most moving. It's, of course, the facts that he taught us, the discoveries he made, the remarkably clever techniques, which are really delightful. They really are. But it's also this irrepressible curiosity, this childlike curiosity, that here we are on this sort of silly, beautiful little rock, and we are reminded how important it is to look out into the universe and ask what else is out there. Thank you.